Hello and welcome to this class on aquifer properties. I am Dr. Shashank Sekhar from Department of Geology, University of Delhi. I will be helping you in learning aquifer properties. Now, what is an aquifer? Let's think in terms of a body which stores and transmits water. That is an aquifer. It stores, transmits, yields in sufficient economic value. It has to yield so much that it can be economically exploited. And in this module, you will learn about types of aquifer, variants like aquifuse, aquiclude, etc., properties which help aquifer to transmit, to store and yield water. Further, you will have a lot of illustrations and exercises, small equations which will help you in learning. Now, let us move to the classroom for further discussion on each of these subtopics. Okay, aquifer properties. Now, before we mention it stores, transmits water and then yields insufficient for economic exploitation. Now, there must be a property which quantifies the storage and transmission. But before we move on to this, let's understand the types of aquifer. How many types of aquifers are there? Now, we have unconfined aquifer. What is an unconfined aquifer? It's an aquifer where at the bottom you have impervious material and the top is open. There is no impervious material. So, rainwater can infiltrate and percolate directly, saturate it and create water table. If you look at figure 1 in your module, it shows an unconfined aquifer where the bottom is impervious and you have one type of material there. Here, the saturation top is water table. At water table, atmospheric pressure equals to hydrostatic pressure. The second type of aquifer is confined aquifer. Now, what is a confined aquifer? It's an aquifer where at the bottom and top you have impervious material. So, it's an aquifer where water is under pressure. The piezometric head, which represents the hydrostatic pressure of the aquifer, is mostly above the bottom of the top confining layer. Let's have a look at figure 2. It clearly shows there that the piezometric surface is above bottom of the top confining layer. Now, you must remember in unconfined aquifer, when you looked at figure 1, the saturated thickness was defined by the water table. Here, saturated thickness is thickness of the aquifer, while piezometric surface is much above the top of the saturation thickness. These are two fundamental differences. Second, if you look at confined aquifer, as you are seeing figure 2, here the recharge doesn't reach the aquifer directly. Rather, there is recharge from far off areas which bilateral flow comes to that place. In these days, you hear a lot about overexploitation. Sometimes you exploit the water so much that the piezometric surface comes below bottom of the top confining layer. In such cases, the saturation thickness changes with exploitation and the confined aquifer hydraulically behaves as an unconfined aquifer. Let's have a look at figure 3. It's a semi-confined aquifer. Here, the top layer is an aquitard, so it allows some amount of water to flow through it. Similarly, we have a purged aquifer. Now, what is a purged aquifer? Look, you have a huge stack of non-indurated sand It's an unconfined aquifer. Imagine there is a crescent shaped clay lens there. What will happen? When the water is infiltrating and percolating, it will do two things. It will saturate the aquifer from bottom to top, and at the same time, what it will do? It will get entrapped in that crescent shaped sand body. Figure 5 is a schematic drawing of purged aquifer. Look at it. You have a vadose zone and a saturated zone separated by water table. In vadose zone, you can see a crescent shaped clay body. Now, when the water is infiltrating and percolating, it gets accumulated in this crescent shaped clay body, creates a local saturation, and that is purged water table shown there. Further, when you drill a well, you should puncture this and go to the main water body below the water table. Okay, by now you are familiar with types of aquifer. Let's come to aquifer properties. In this aquifer properties, we will first have porosity, which is most fundamental. Now, what is porosity? Porosity is measure of volume of voids, the space occupied by empties, to the total volume of rock or formation. You have a look at equation 1. You have N, which is porosity. In numerator, you have VV, which is volume of voids. In denominator, you have V, that is total volume of rock. Mostly porosity is expressed as percentage. That's why you multiply by 100. Now, porosity can be either primary porosity or secondary porosity. Have a look at figure 6. What is there? You have porosity, flow chart, primary porosity and secondary porosity. It's written, primary porosity is porosity formed during genesis of the formation. Secondary porosity, porosity formed after genesis of the formation. Like sand sap porosity, which is primary porosity. Limestone fractured have porosity, which is secondary porosity. Porosity is a function of sorting, packing, shape and fabric of the grain. In case of secondary porosity, it is fracturing, etc., which matters. Okay, the next property is effective porosity. Now, what is this? What is this effective? Added before porosity. It's a measure of volume of interconnected pores, because in water science what matters is flow of water, and that is where interconnected pores gain their importance. So effective porosity is a ratio of the volume of interconnected pores to the total volume of rock or formation. You have a look at equation 2. It is explained there. Here E on the left is effective porosity. Vi in numerator is volume of interconnected pore space, voids. V in denominator is total volume of rock. It's as simple as that it matters in transmission of water. Yes, there, you shouldn't be sleeping. This is a monotonous class on aquifer properties, and the next is a specific yield. Now, what is this specific yield? I think you remember we talked of yield of water, and this is a specific yield. It's the volume of water which is drained out of the aquifer that matters to us. Volume of water drained out of the aquifer under influence of gravity to the total volume of the formation. You have a look at equation 3. There you have Sy, which is a specific yield on the left, and in numerator you have Vw, that is volume of water drained under the influence of gravity, and in denominator you have V, volume of the aquifer. Have a closer look. If you have a closer look, there is no unit. It's dimensionless. A specific yield is dimensionless. And it's not over yet. You have many more. And the next is a specific retention. You shouldn't be talking only of yield. So we have a specific retention. What is that? Volume of water retained against the force of gravity to the total volume of the formation. Have a look at equation 4. On the left, you have SR, that is specific retention. This equals to VR, volume of water retained against the force of gravity, divided by V, total volume of rock. You will again examine there is no dimension here, it is dimensionless. Further, if you have a look at equation 5, where we add a specific yield and a specific retention, what you get is porosity. So, the addition of a specific yield and a specific retention is porosity. The next is a storage coefficient and a storativity. These are storage parameters. Now, what is storage coefficient? Volume of water released or taken in by an aquifer through unit cross-sectional area under influence of unit decline in head. So, it is volume by area multiplied by change in head. Again, it is dimensionless. Have a look at equation 6. Here we saw SC, that is storage coefficient. This equals to VW, volume of water either taken in or released by the aquifer, divided by A, area of the aquifer, and delta H, change in hydraulic head. In case of confined aquifers, this storage coefficient is often referred to as a storativity. Okay, we just finished a storage coefficient. Now, yet there is another storage parameter, a specific storage. This is defined as volume of water which comes in or comes out of the aquifer per unit volume of the aquifer per unit change in head. It's best expressed in equation 7, where VW is the volume of water drained. In denominator, you have V, that is the volume of the aquifer, and delta H, that is change in head. In confined aquifers, if you look at equation 8, we have S, that is storativity, equals to a specific storage SS into B, saturated thickness. We just finished a specific storage, that is the last storage parameter. Now we will start with conducting or transmitting parameters of the aquifer, and the first is hydraulic conductivity. Now, what is this hydraulic conductivity? Very important in hydrogeology. Everybody discusses about this. It's volume rate, that is volume per unit time of water conducted through an aquifer, and water of given kinematic viscosity through unit cross-sectional area under influence of the given hydraulic gradient. If you have a look at equation 9, it elucidates the concept of hydraulic conductivity. K on the left is hydraulic conductivity. On the right, Q in numerator is volume rate of water. A in denominator is the cross-sectional area which is at a right angle to the direction of groundwater flow. Delta H upon delta L is hydraulic gradient. Now, this hydraulic conductivity has dimension of L T minus 1, that is meter per day. It is a function of media and fluid both. Hang on, hydrogeologists don't live like this. They demanded there should be something which is a property of media only, and then came the concept of intrinsic permeability. It is a function of the media only, irrespective of the fluid. It is given in equation 10, where you have CD square. D is diameter and C is a proportionality constant. Further, if you look at equation 10, this proportionality constant is dependent on grain size, sphericity and roundness of the grain. D is diameter, already mentioned earlier, and the unit is Darcy. If you go ahead, and what is the relationship between hydraulic conductivity and intrinsic permeability? We have equation 11, where on the left, K, that is hydraulic conductivity, equals to small k, that is intrinsic permeability, multiplied by rho, that is density, multiplied by g, that is acceleration due to gravity, and the whole divided by mu, that is kinematic viscosity. Okay, we need not run away. Still we have some more properties, and that is transmissivity, yet another transmitting capability. What is that? Transmissivity is very much related to hydraulic conductivity. Now, it is volume rate of water transmitted through unit saturated width, not area, and the width at a right angle to the direction of groundwater flow under influence of given hydraulic gradient. The unit is meter square per day, that is dimension L raised to 2 T raised to minus 1. Both of these, transmissivity and hydraulic conductivity, can be related through mathematical equations. Let's have first look at equation 12. Here T on the left is transmissivity and Q is volume rate of water. This is divided by W, that is saturated width of the aquifer, multiplied by delta H by delta L, that is hydraulic gradient. Now equation 13 gives a relationship between hydraulic conductivity and transmissivity. How? It divides the first equation 9 and then equation 12. What you see in the end is equation 14, which says that T, transmissivity, equals to K, hydraulic conductivity, multiplied by B, saturated thickness. If you have looked figure 7, it's very clear that W is the width and B is the saturated thickness. Let's summarize. We discussed about aquifers, formations which store and transmit water. They also yield insufficient for economic exploitation. We have aquicludes, which are only porous, not permeable. We have aquitards, which are porous with limited permeability. We have aquifers, neither porous nor permeable. Then we discussed about types of aquifer: confined, unconfined, semi-confined, and purged aquifers. Then we went to aquifer properties. We started with porosity, that is volume of void vis-a-vis volume of formation. Effective porosity, volume of interconnected voids vis-a-vis volume of formation. Specific yield, volume of water drained under influence of gravity to the total volume of formation. A specific retention, volume of water retained against the force of gravity to the volume of formation. Storage coefficient, volume of water released or taken in by an aquifer through unit cross-sectional area by unit decline in head. hydraulic conductivity, volume rate, not volume, of water transmitted through unit cross-sectional area under influence of given hydraulic gradient, and then we came to transmissivity, volume rate of water transmitted through unit saturated width under influence of given hydraulic gradient. In both cases, hydraulic conductivity and transmissivity, kinematic viscosity of the fluid has to be same. That's all. Thank you.